In this second part of my introduction to high-order harmonic generation, I will more focus on the macroscopic aspects of this process. And there will be two parts. First, I would like to discuss the scaling laws of high-order harmonic generation, in particular the geometrical scaling, and then I will talk about phase matching. So let me start with the geometrical scaling. Here you have a wave equation describing the generation of high-order harmonics with on the second part of the equation you have the polarization term, and here you have a propagation, diffraction, and dispersion. So now if you make a scaling, if you scale this equation with, for the z parameter eta square, for r parameter eta, this double derivative with respect to the x and y will varies as 1 over eta square. The dispersion term is proportional to the atomic density. Let's assume that the atomic density is also proportional to 1 over eta square. And finally, the polarization varies linearly with the density, which varies as 1 over eta square. You see that all of the terms of this equation varies as 1 over eta square, which then can be factorized. So now if you generate with a certain input energy, you would like to keep the same intensity in the medium when doing this scaling in order to have the same polarization. So if you want to keep the same intensity, you have a W here, which is the spatial dimension of the interaction, and which varies as eta square. So you need to vary the input energy with the same factor eta square. So this leads to the following scaling. Let's consider a certain harmonic generation process with an input energy E in and a certain density rho, length of the medium L, and a focus with a radius W0. You can scale this interaction by multiplying the length with eta square, the radius with eta, divide the density by eta square, multiply the input energy by eta square, and you will get exactly the same interaction, and the output energy will be multiplied by the factor eta square. So in other words, the conversion efficiency of the process E out divided by E in is completely scaling invariant. This equation that you see here is mathematically scaling invariant. And using this scaling, you can understand why the harmonic generation has been performed in so very, very different conditions, from very long setup to much more compact setup. And you also understand how it is possible to get high energies if you have high input energy and if you scale the setup appropriately. And just to illustrate what I just said, I present here pictures of experimental setups that we have in LUND. We have a long harmonic generation setup with a footprint of about 15 meters, where we use an intense laser with a lot of energy per pulse to generate high-order harmonics using a long focusing geometry. And on the other hand, here we have a much more compact setup, where the laser is in this box here, and the setup is very compact, using tight focusing, but reaching similar intensities in the laser focus so that the efficiency is the same. So that means that high order harmonic generation can be performed with a relatively high average power if you use this type of system, where you can use laser with very high repetition rate, a few hundred kilohertz repetition rates, or with high energy per pulse using lasers with high energy per pulse, maybe lower repetition rates, 10 hertz or a little bit higher. It's not possible to talk about scaling of high order harmonic generation without talking also about the wavelength scaling, which is for the single atom response. And simply the photon energy that you can get varies as a product of the laser intensity times the square of the wavelengths. And this means that if you use low wavelengths, like mid-infrared laser system, you can get very high order harmonics and very high photon energy, as is shown in this picture, showing the range of harmonics as a function of input wavelengths and reaching photon energy of a few hundred electron volt. Now let me conclude this introduction about high order harmonic generation by talking about phase matching. What is phase matching? Phase matching is about making the phase difference between the harmonic field which is generated and the polarization, the phase of the polarization equal to Q times the laser phase equal to 0. And you can express this with the help of a difference between the phase mismatches or the difference between the refractive index at the frequency of the fundamental and the frequency of the harmonics. So it's about making the phase velocities of the harmonic field and the fundamental field equal to 0, being equal. In our problem, the phase mismatch has 4 contributions. One is due to the neutral atoms, 1 to the free electrons, 1 to the focusing, and finally 1 to the electron trajectories. So let's discuss these 4 contributions. The contribution of the neutral atoms can be illustrated by this plot showing the refractive index as a function of frequency over a very large range. The refractive index for the laser that we used in the visible or near infrared is always larger than 1, while the refractive index for the harmonics that we generate is less than 1. So really shows that if you only consider neutral atoms, phase matching cannot be realized. And this is so the phase mismatch, because of dispersion in the neutral medium, is always positive. Let's consider the effect of the free electrons. The phase mismatch, because of the free electrons, can be expressed by this term here, where eta Fe represent the degree of ionization in the medium. That's very important quantity to understand phase matching. Typically, in this process, it's of the order of a few %. This term is always negative. The effect of focusing comes from the variation of the QU phase. So the phase mismatch can be expressed as Q times the derivative of the QU phase, which you have here. When you are close to z equals 0, this expression is very simple, minus Q divided by the Rayleigh length. It's always negative. And finally, the effect of the dipole phase. So this is really the effect of the phase accumulated by the electron on its trajectory, which is then transferred to the harmonics. So this phase mismatch is equal to the derivative of the dipole phase. And now I'm looking at how this dipole phase depends on z. And similarly, I can introduce the derivative of the intensity with respect to z. And what I get is that I get a minus sign here and a derivative with respect to z, which is proportional to z. So this is actually very close to 0 when z is close to 0. So when the medium is generated close to the focus of the laser. So we have in total a contribution which is positive from the neutral atoms, 2 negative contribution, and then a contribution which is very close to 0. So I'm not going to talk about this anymore. So you can see that to achieve phase matching, we need to have this sum here equal to 0. So here you have 3 terms. The first 2 terms, dispersion due to the neutral atoms or the free electron, depends on the pressure, while the third term does not depend on the pressure. So you see that by solving this equation, you can extract a phase matching pressure, the pressure which is needed to achieve phase matching. And this is a plot of this phase matching pressure as a function of ionization degree. I'm not exactly showing this phase matching pressure, but the phase matching pressure times the Rayleigh length. This is to account for this geometrical scaling that I've introduced before, and that makes this plot geometry independent. So what is shown here is this phase matching pressure for 2 different gases and different harmonic order. You have 23 and then 21, 19, and similarly around the 69th harmonic in neon. So you see that the phase matching pressure is rather constant for low ionization degree, and then it goes to infinity for a certain ionization degree. And this ionization degree here is called the critical ionization. It happens when the phase mismatch, because of the neutral atom, is equal to minus the phase mismatch due to the free electron. And in this case, the phase matching pressure goes to infinity. And when this happens, we call this ionization degree Mach. So this is the expression for the phase matching pressure, the expression of these lines, which is indicated here. Now, when discussing macroscopic aspect, it's very important to discuss the influence of absorption, which was actually pioneered by a work of Eric Constant many years ago. So let's introduce the absorption length, which is indicated here, which depends on the ionization cross-section, and the coherent length, which is pi divided by the phase mismatch. We can plot the harmonic intensity as a function of length expressed in a unit of the absorption length. And you can see that you have different type of behaviors depending on the ratio between the coherence length on the absorption length. We can start by the blue line here, which means basically that you have no good phase matching and you have an oscillations, which means that the harmonic field do not grow in the nonlinear medium. And the case which in yellow is for an infinite absorption length, but you have different cases. An interesting case, maybe it's a case where the coherence length is equal to 4 times the absorption length, which means that there is a good phase matching. And you see that if you follow this line, that you see that then the length of the medium, you don't need to have a very long medium length, but the length of the medium equal to 3 times the absorption length is actually a good condition to ensure a large harmonic yield. So we need to have coherent length larger than typically 4 times the absorption length, and length of the medium larger than 3 times the absorption length. So now let's me discuss combine what we have learned regarding the phase matching pressure and how the length of the medium should be chosen. And here I'm showing simulation about representing the conversion efficiency in argon for the 23rd harmonic using 800 nanometer wavelengths. And what you have here is, so this conversion efficiency is in color, and it's as a function of pressure and medium lengths, again in these scale parameters which account for the geometrical scaling. So pressure times the Rayleigh length, and medium in unit of the Rayleigh length. This is for an intensity of 2 times 10 to 14 watts per square centimeter. And you see that this conversion efficiency actually is pretty much constant on a hyperbolic curve that you see here. It reaches a little bit below 10 to minus 5 in argon. So in other words, it's possible to generate high order harmonics with approximately the same efficiency using either high pressure and short medium lengths or low pressure and long medium lengths. You can reach similar intensity. This really shows that this process is very universal. It can take place in very different type of conditions. The vertical branch of this hyperbole correspond to conditions where phase matching is achieved in a transient way, and where what matters is the amount of free electron in the medium. So you need to make this equation close to zero, and it's very weakly pressure dependent. However, the horizontal branch is the case where the free electron contribution is not so important, lower laser intensity, and where this equation is achieved to obtain phase matching, weakly length dependence. You can also write an expression for this hyperbole, which I am showing here. If you are interested by details, you can look at this article. So this is the expression of this hyperbole, where the P0 here it is given by this quantity. And again, you see that this depends on essentially two parameters, the absorption cross-section and this ionization degree, which corresponds to the critical ionization for the gas. And this concludes my introduction. Thank you.